Hello, welcome to the stream. This is going to be another chill math stream, and Larute is the winner for first in chat this time. Let me just quickly react to that with some sort of appropriate. Oh gosh, I've been trying to learn about emoji, the emotes in Twitch chat. Let's try and get. Yeah, no, I don't know. Oh, and some sort of cookie monster is here. Good. Okay. Oh, that's not good. That is not syncing properly with the thing. 2 seconds while I set up my stream chat. How are you doing in chat, everyone? You alright? Oh, I got a sub! It's Cookie Monster! Thanks for the sub, Cookie Monster. Good stuff. That is a good use of a Prime sub. Every subscription to this Twitch channel goes to charity if I eventually get enough out of this that they get back to me. Oh, gosh. Yeah, we're on half term. That is good. Half terms are weirdly spread out this year. People have got different half terms at different times. That's not working the way I thought it would. So I'm just going to go in and try and reset that. Oh, sorry, we've gone a bit dark. That's not what I wanted to do. Oh, tech, you know. What's tech like? This is why we practice technology first. Let's try and reconnect it. Okay, let's try and how do I do this? Turn it off and on again. Yeah, let's turn it off and on again. Oh, that's really weird. It's not done that at all. Okay, so people watching at home, usually that's connected to rebroadcaster screen that I've got, and it is instead taking a screenshot. So we're going to do some switching it off and on again. Screen is going to look like this for 2 seconds, but I'll keep the microphone on while I try and work this out. Great, an offer in chat for, oh my goodness, what a long post. Someone in chat has picked this moment of all moments to try and offer me Twitch promotion. So you know that's exciting. Yeah, but I know, but still. What happens if I can't get the screen to do the thing? We close the thing, reopen the thing. Oh, this is tech like we've never had it before. Everybody loves tech. Now are you going to work? No, not going to work. Still not happy. Oh, what is this rubbish? Just want to rebroadcast. It shows the print screen. It shows the screenshot, but not the thing. Right, cool. We might be switching to a sort of backup tech. Fun times. I'm going to come back on screen. The bot's just disappeared off the top of chat. My screen's gone! Nothing's perfect, is it? Good afternoon, Asher893. Nothing's ever perfect. Oh no, this is not a bot post. You just have robots in your post. Oxford University, yeah, derivation heat equation. Not typically interesting in applied maths. Here's the thing. Lots of people think they're not interested in applied mathematics, and then it turns out that if you're good at the sort of, I don't know, my path was I thought I was really into pure mathematics, went to university, did some pure mathematics, did some applied mathematics, realised I was much better at applied mathematics than I was at pure mathematics, and that made all the difference for me. Hi, if you've just joined us, I have the following tech issue. That I've got my screen linked perfectly to my computer. I can't get OBS to pick it up, so I'm going to switch to a backup solution, but also talk to chat at the same time. That's the kind of multitasking that we do around here. How do I want to play this? How am I going to play this? We're going to go here, and we're going to go to Desmos. If in doubt, open Desmos. That's what my gran always says, right? So do I do this? But then select, and then cut? Yeah, there we go. Cool, good. Okay, if in doubt, Desmos. Good. Now we got Desmos. Now what? We've also lost the chill maths thing that's normally on screen, right? It normally says chill maths there. Why does it not say that here? There we go. Oh my goodness, it's all happening today, isn't it? All happening. There. Oh, it's like negative. Chat, I don't know what's going on. Oh, right, okay. Matt stuff. I have an alert for this one. I've also set up CloudBot. I'm really not keen to talk about the map. I will do a tiny bit for just for you because you were the first person you didn't know. I'm currently writing, in my job, I'm currently writing guidance for tutors. One of the things I'm putting in the guidance for tutors is that you should not be disadvantaged if you take the mini-mats. That's all I'm going to say about the mini-mats, that you should not be disadvantaged. It's been a lot of work to set up, in a week, to set up and invent an entire extra test. Well, that's basically like the mat, set it all up and get it ready for about 1,000 people to take it. That would be a complete waste of my time if it was a disadvantage. If the correct play was to ignore me, then I'd be very, very sad. I think anyone can trigger that, by the way. I set up a few. So I've got the normal ones, like uptime, which tells us that we've been somehow wasting 6 minutes and 22 seconds of people's lives so far. Sorry about that, chat. And we've got some of the other normal ones as well. I hope everyone can see the Streamlabs thing. It's this incredible tech where it's not even really part of Twitch. It's just like some external service that follows your stream, and then if you shout at it with an exclamation mark, it'll do stuff. No worries. What I'm going to do is, try and avoid talking about my job, I'm going to do exclamation mark stuff. Right, okay. Here's the plan for today. Or at least a little bit of plan for today. Sometimes during the week, I take notes on things that have turned up that are interesting to me, things that I want to look into, but things I don't have time to look into, so that I can talk about them on here. That's kind of my plan. I found a cool link that I want to talk about. A thing that I want to show you. My plan was really to write some stuff first. I'm gonna, in the background, try and get that working. Does the commands thing? Okay. So the neutrinos typed exclamation mark commands, which I think should do something like tell you what the commands are, but it hasn't done anything. So maybe that's on me. Okay. I wanted to talk about perfect numbers. Desmos can't really help me with that, right? So maybe I think the place I want to get to is to try and understand this page that I found. It's linked to from a Wikipedia page, and it's the Euclid-Euler theorem. The idea is that you can characterize these even perfect numbers. So kind of my plan for today is maybe to tell you what one of these is, and then to try and maybe work through this proof that's on this website. The punchline is supposed to be that all perfect numbers that we know of are triangular numbers, which is kind of cool. You know what triangle numbers are from school. Perfect numbers you might have come across before on a number file video or something. But there's this proof that all the even perfect numbers are triangular numbers, which I don't know, just tickles my funny bone a little bit. Have I got to list my commands somewhere? Laroot's going to help. And I also have had this weird idea that putting an exclamation mark in front of a number means something different. I don't know how to look that up, but maybe you at home could look up. I think exclamation mark n is different from n exclamation mark. Oh, which mug have I got today? I've got the Pusheen one. It says I love kitties on it, and that's got all the different. That one is actually Pusheen, right? Cats. It's not all great waves. I really want to know why I can't capture the screen. I'm still on that. And it's very tempting to just fiddle with that for the next 2 hours, right? Is it a hardware acceleration thing? 2 seconds. I'm going to keep doing that. Okay, so I think first I need to say a little bit about what perfect numbers are, and then say a little bit about this thing that I learned about even perfect numbers a long time before we get down to the other way round. I am going to go for the incredibly wonky backup option. Didn't really want to do it like this, but we are going to do it like this. This is professional. No, this is the unprofessional stream. I've now listed them properly on my website, so my website now describes a professional live stream and an unprofessional live stream. Plonk this on here, and that should now broadcast to you. Good, yes, okay. Okay. Oh, this is going to be so bad. No, we can do this. This is going to be fine. It's going to be fine. Never overestimate, never underestimate what's going on. There we go. That's quite nice, actually, isn't it? It's just, okay. So, perfect numbers work like this. 6 is an example of a perfect number. It's 1 plus 2 plus 3. These are the factors of 6, and they add up to 6. That's kind of nice. I mean, 6 is a nice enough number. The next one up, I can't really remember when I learnt this, but the next one up is 28. 28 is 1 plus 2 plus, oh gosh, the factors of 28. It's a multiple of 7, so you get this 7 in here. It's also a multiple of, oh gosh, 14. There's this good way to check if you've missed factors, that check you don't miss any, is that whenever you list a factor, you should also list the other one that multiplies together to give 28. Here are the factors of 28, and they add up to 28. Now you might have noticed that there's something slightly odd going on here, that, well, these aren't all the factors of 6, are they? Because in a very real sense, 6 is also a factor of 6. But that makes it not true. The kind of cute thing that you could say is that that's 2 times 6, and this is going to be 2 times 28. So there's 2 ways to think about perfect numbers. One of them is that a perfect number is made up of the sum of all of its proper divisors, where proper divisor means something like not including itself, which is kind of quite nice. Or you could think about a perfect number being twice that number is equal to the sum of all of its factors. Both of those feel slightly off, right? Just a tiny bit off, in the sense that I guess what we really want is something like, so let's make this huge. Why not a perfect number is equal to the sum of all its factors? That feels like even more perfect. Even more perfect, right? Up here we've got numbers which are equal to, the sum of their factors is twice the number, and those are called perfect numbers, but it feels to me like they'd be even more perfect if it was, all of them adding up to the number. Chat, what do you think about that? Both of these definitions have got something slightly awkward, which is you can have, let's draw a rectangle. You can have this fact around here. Oh, 28's off the screen. There we go. My screen is 4.3, and that one is 16.9. Sorry. You could have that fact, or you can have this fact. But you have to include the two, or awkward. Chat thinks that this is not a good definition. Because every number has 1 and itself as factors, which is quite bad. That means that the sum of all its factors is almost always larger than the number. Chat has got, right, okay. 1 is a good example, Larud and Neutrino, good stuff. 1 is an example where, okay, that would be perfect under my new definition. So my new definition is rubbish. It only permits 1 extra perfect number. Nothing else. But this is still a useful thing to think about, because this opens up the idea that, okay, for every number, so this didn't go anywhere. Maybe 0 to if you include the negative factors. Yeah. Well, then I think only 0. Only 0 if you count negative factors as well. So this idea didn't really go anywhere, but it does open us up to the idea that the sum of all the factors of a number is, except for 1, always larger than that number. What if it's exactly twice as large? This is kind of the idea behind perfect numbers. Now, there's there's other things we could think about, right? So we can think about, could it be 3 times as large? Could it be 100 times as large? Some of these feel a little bit unlikely. Some of its factors being 100 times as large as the number. That feels unlikely because the factors are all smaller than the number, and can a number have that many factors, like, all of which are quite large? For 28, one of its factors is 14. How large can the sum be compared to the number? Something I like to do when I'm trying to understand something new is ask myself questions. And the questions might turn out to be stupid questions, or just questions that don't go anywhere, like, can we make extra perfect numbers? But sometimes they force me to understand what's actually going on, or what's actually real. Sorry about the really loud keyboard noises. It's not really my plan for the stream, but here we are. Right, LaRue's got a bound in chat, which is based on the triangle numbers, I think, for summing up what if everything is a factor, which seems pretty unlikely, right? Seems pretty unlikely, but a good start. That the sum of, okay, so you've added up all of the numbers up to n, and you've told me that's 1/2 of n plus 1, which is pretty large. It's n plus 1 over 2 times as big as the number. Well, I suppose I don't really believe that you can get that large, so I agree that's an upper bound. It depends on n, but I guess I'm not currently convinced that you can get anywhere near that. For example, you can't have any factors bigger than half the number, right? You always have to have a jump up from, if your number's even, half the number will be a factor, but then you can't have a number in between for the factors. Like 28 is just not a multiple of anything between 14 and 28, because what would the quotient be? What would the thing that you multiply be? So maybe we can do slightly better. But maybe the answer to this question, so maybe arbitrarily large? Maybe. Remember that I can set up commands during the stream, which is also fun. There's sort of too many things at once. Maybe I shouldn't be doing it. Maybe I shouldn't be doing this. Because I also set up a who, what, where, when thing. So we can go, so if new people come in halfway through, which happened a lot last week, you can go what, for what are we doing? And we're investigating perfect numbers. But I have to keep updating it, and I don't know how to do that quickly. Twitch is, as always, a mystery to me. Right. So maybe arbitrarily large. And a good thing to do perhaps would be to try and find some examples of numbers which have a really large sum of factors. Well, we can come back to this idea that the sum of factors landing perfectly on twice the number. Perfect. Number of distinct prime factors. Yeah, sure. Okay. If you've got a lot of prime factors, then you generate a lot of factors of your prime factors. Let's see then. Let's think about the smallest prime, which is 2. Let's think about powers of 2. So these numbers 2 to the n. Now their factors, including the number itself, are 1, 2, 4, and so on, up to 2 to the n, including the number itself, with some... I can't believe I've been reduced to this. Drawing with mouse. Have I really got nothing better to draw with than scribbling with a mouse? No, I think it is true. I think that's what I've got. People hate this. So it's not how you do an effective stream. If you do that sum, what do you get? That's a geometric sum, right? Yeah, it's like 2020, yeah. It's like early pandemic. It's just so ugly, right? And so wide. Why am I going so wide? My hand-eye coordination is rubbish. You get this geometric sum, right? Which is slightly less than twice as large. So I thought this would be a fun place to look, but oh no, it's actually kind of rubbish, right? I thought this would be a really big sum because I thought powers of 2, there's lots of factors there, and I know what the factors are. But the sum is slightly less than twice as large. It's rubbish. It's not as good as this 6 at the top here, where 6 had a bunch of factors as well. So I guess maybe I want to think about primes. So when I'm saying twice as large, I'm comparing this number to the original starting number. And because of the -1, it's slightly less than twice as large. So disappointing there, as things sometimes are. Oh, P prime. I'm actually going to resort to a text box. This is now just me typing a live stream. Amazing. Let's go factors. Oh, this is even worse. The sum is 1 plus p, which is only slightly larger than the number itself. Oh dear. So this is not going terribly well for me finding numbers with a large kind of a large sum of factors compared to the number. I have to say compared to the number because you get a large sum of factors just by choosing the number like a million, where the sum of factors includes 1 million. So now look at a billion. Oh, the sum of the factors includes a billion, so it's bigger than a billion. I suppose what I really want is to know when you have a number and it's prime factorization, what's the sum of the factors of that number? We can build up to it, I suppose. Yeah, let's build up to it. I like to think about PQ next, for if something's got number PQ with P and Q primes. A large power of 2 multiplied by a large power of 3. Yeah, we can get there, I think. I want to two-step it. I want to do PQ first, to think about PQ, and then sure, we can throw in like some 2CNs and 3s. Or maybe Nexinator, I think. Yeah, you get combinations, don't you? Because if you've got a large power of 2 and a large power of 3 multiplied together, then the factors look like some power of 2 and some power of 3. So, what's going on here? P and Q with P and Q primes. I think I want to list out the primes and then show you a kind of trick, which I don't know if it's obvious or not, but so the sum is 1 plus P plus PQ, and that factorizes. That's equal to, oh gosh, we will overcome. Is this some sort of like curse? Am I cursed to just have terrible live streams? Roll up. Some idiot trying to work out how to use. Some idiot trying to work out how to use technology. It's supposed to be a stream. It's supposed to be a sort of thing. Might not always appear to be, but it's supposed to be a thing. Oh my goodness. Right, okay, bear with me, chat. We're still trying. We're also frantically turning stuff on and off again so I can give you an actually good experience. Oh, has it done a thing? No, it almost did a thing and then it didn't. I think I've got to disable hardware acceleration in something random, which is not a phrase I want to use during a live stream. Okay. So this shows me that if I set my primes up right, then the sum relative to the number. So compared to number, the kind of ratio here is like 1 plus p, 1 plus q divided by pq, which is like 1 plus 1 over p from the first bracket, changing the order of the terms, sorry, and 1 plus 1 over q from the second bracket. So if I make the primes small, then these numbers are quite big. So if I use 2 and 3, well, 2 and 3 would give me the number 6, which we had earlier. But this would be 3 over 2, and this would be 4 over 3. So you see those are two fractions, they're both bigger than 1. That could maybe sort of multiply together to give me something larger. Still not convinced. Can I make that larger? No, 2 and 3 are the smallest primes I can think of. So I still haven't found anything where the sum of the factors is bigger than 2 times the number. We go again. Oh, it's actually got worse. The tech thing, which I've been trying to fiddle with and fix in the background, has actually got worse. That's great. That's real helpful. Wait, screen capture is the answer. Screen capture is the answer. Yeah, it's dangerous, but we can do it. We can do this. Is this a proof that 6 is... Oh, hang on. Yeah, I suppose it is. Cookie Monster, I like the way you're thinking. Huh. This is a proof. If you want that to be 2, if you want that to be the number 2, with P and Q, both distinct primes, should probably said distinct primes. It's slightly different if they're the same prime, because I would have... Anyway, never mind. But if P and Q are distinct primes, then the only way to make that 2 is to... Huh, yeah. That's really funny. I like that a lot. Okay, cool. Good news, chat. The only perfect number that's the product of exactly 2 primes is 6. Fact from chat. Oh no! I read out the wrong name. I'm so sorry, Nexonator. Oh dear. Absolute disrespect. Sorry. How do I pin? There we go. You get a pin. There you go. It's like sort of payback. It doesn't show up there. We've pinned you for 20 minutes. I'm so sorry. Right, good. Okay, but with my other arm, moving around Windows frantically, we're going to do this, we're going to do this, we're going to do this. We're going to get some actual tech going. It's going to be good. It's going to be good. Window, screen capture. Screen capture. Screen capture is the answer. Not that one. That one. Yes. Yes. This is perfect. Bring it down. Chat, this is what we've got at the moment. We've got my actual thing I can write on. I'm going to bring it down here. Down here, yes, perfect. Underneath, make it larger. Move it around a little bit. Pin it. Right on it, yes! We fixed the tech. We fixed the tech. Stop the clock, it's 2:30. Nexonator. So Nexonator theorem. 6 is the only perfect number. No, wait. Only perfect number of the form PQ with P and Q distinct primes. Proof. Proof works like this. If n is equal to pq, the factors are 1 p q pq distinct. So if you need p and q to be distinct, so this isn't a list of the same factor twice, and the sum of those is 1p plus q plus pq. Question: is that 2pq? Only if, and this factorizes 1 plus p 1 plus q is equal to 2pq. So only if, and you can divide by p to get 1 over p plus 1. 1 over q plus 1 is equal to 2. Isn't this so much better? Technology! The handwriting's actually got worse. But, oh no, 1 plus 1 over p and 1 plus 1 over q are, well, they're either 3 over 2 if p is 2, or 4 over 3 if p is 3, and those ones multiply together to give 2, or if p is bigger than 3, so p is bigger than or equal to 5, just sort of spelling it out, then 1 plus 1 over p is less than 5 over 4, no, 6 over 5? Less than or equal to 6 over 5. I suppose I need to check what if one of them is small and the other one is enormous. Yeah, so there's this, say that p is less than q to make it slightly easier up here. Trying to put together the proof for Nextnator. Yeah, sorry. I don't really know if it's etiquette to read out people's usernames in chat or not, but you know, you gotta live with it now. It's got a theorem on it. Oh, I love this stream sometimes, all the time. Okay. 3 over 2. So there's like several cases to kind of check. I'm just a little bit nervous. If p is 2 and q is not 3, or if p is not 2, q is like maybe 3, and then if p is, am I making too much of a thing of this? Times, and then this thing is greater than equal to, this thing is less than or equal to 6 over 5. 18 over 10, 4.8. If p is not 2, then it's this term is less than or equal to 4/3, and this term is less than or equal to 4/3, which is 16 over 9, which is less than 2. Okay, and finally, yeah, okay. Yeah, these are my two cases. Okay, we did it. I think, more or less. There's some cases to check. Do you want Zoe's theorem? I was going to say we need more theorems named after Zoe. People called Zoe should have like priority for naming theorems. But then, as I was about to say it, I thought, wait, no, we need more theorems named after Nexinators. I can't think of any theorems named after Nexinators. So sorry. Right, cool. Okay, there's one element of this thing. The reason I wrote most of this out is the way this sum factorizes. It is kind of cool. So this step here, the way the sum factorizes, theorem privilege. Yeah, umlauts. There's quite a lot of umlauts in theorem names already, but yeah. Okay. The way this factorizes is a clue to something else we can do. That in general. So let me show you an in general kind of thing. The sum of the factors of n factorizes. I don't really know if people know this already, whether this is the sort of thing that everyone knows, but it's quite useful for those sort of like sometimes BMO problems, Maths Olympiad stuff. The sum of the factors of a number factorizes. Ooh. Wait, you say they changed the... Oh, changed the syllables. Okay, right, good. I'm learning about dots. I work with a Zoe who doesn't have any dots, which I think means that... I think Zoe without any dots has to... Maybe you're technically supposed to pronounce it differently, but we'll call her Zoe. Anyway, so e.g. 28 again, our old friend, is 1 plus 2 plus 4 plus 7 plus 14 plus 28. That's got kind of two groups of factors. It's got ones that aren't a multiple of 7 and ones that are a multiple of 7. So you can kind of split it down to, would you like your factor to contain a 7 or not? Those are the choices in life. Brilliantly, these terms over here, once you've decided to put a 7 in, these terms are 1 times 7, 2 times 7, and 4 times 7, exactly the same as over here. Let's make it slightly clearer. This is 1 plus 7, and this is 1 plus 2 squared, which you could think of as being your choice of how to build a factor. So your factors of 28, which is, so 28 is 2 squared times 7. The factors of 28 like this. They can't have any 3's in, that would be silly. 28 is not a multiple of 3, so 3 is right out. But they could have some 2's and 7's in, not too many. Don't get carried away. Like, factor of 28 can't be like 8 or something. But you could have a 7 in there if you want. Not 2 7's, but you could have 1 7. So these are kind of your choices. And you make those independently. Your factor has to be 2 to the A, 7 to the B, with somewhere between 0 and 2 powers of t, multiple factors of t, and somewhere between 0 and 1 factors of v. Okay. Do I need to put a cooldown on the what thing? Larude got that. Okay. Larude's learning commands. I've set up commands. I'm very pleased with myself. Yeah, okay. Maybe I need to put a cooldown on the thing. What? I set up the others as well. So if you have other one-word, oh god. I thought that was useful. Because now it just looks really sarcastic that Streamlabs she keeps going, oh, numbers. You're asking purple numbers. Brill. I set up other one-word questions. You can try and find out what they are if you like. Okay. There's a general pattern here, which you can maybe see how to extend this. So, if your number is, I want a better example. If your number is like factors of, what's got a lot of factors? Factors of 60. Which is, quick reminder, 60 is 30, is 2 squared times 3 times 5, I think. They are, you could have some 2's in there. You don't have to have any 2's in your factor, it could be odd. You could have some 3's, and you could have some 5's. And this gives you a quick way to work out the sum of the factors, which is the sort of thing that we want. Wherefore and how? These are good ones for next time. Let me write that down. Wherefore requested, and also how. I did think long and hard about how. If you have a suggestion of what the how command should do, and let me know. Anyway, this gives us a nice shortcut, this idea, because now, instead of writing out all the factors of 60, I can just write down this neat factorised form that has all of the factors of 60 in it, and is perfectly set up for me to come in and divide it by 60, right? So the ratio of that sum to 60 is 1 plus 2 squared, and I'm going to divide by 2 squared, 1 plus 3 over 3, 1 plus 5 over 5, which is not great, is it? It's 1 plus a half plus a quarter, 1 plus a third, 1 plus a fifth. But maybe this is a route to making quite a large sum, because I can see this getting quite large, right? I can make this larger and larger. I guess how large can I make this term? We sort of tried it before, didn't we? That's 7 quarters at the moment. Okay. So this is a good way of working out the ratio of the sum of the factors to the number itself. You can actually simplify this quite a bit without doing much more work. This gives me, this is, the 4's cancel. The 6 gives me 14 over 5, which is almost 3. So maybe this is a good way of working out how large these are. Yeah, if this is good for the BMO, then, you know, remember where to use your prime sub, eh? Remember where you learned about perfect numbers. Oh, by the way, I once proposed this. Oh, it's too close to my job, but I once proposed this for an interview question, but we decided it was too well known. I say we. It was a team decision that we thought it was too well known. I'm not sure it's very well known, which is why I'm telling you now. Okay, fine. Like, I have to sort out a lot of maths, right? Lots of maths get sorted out into, not many people know this. I could use it for an admissions thing. Versus, not many people know this. I could tell them on a live stream. It's important to separate those things. So once we decided, not very many people know this, but we're not going to use it for this interview. Here we are. Throw down the Nexinator's theorem. See what the examiners do. Yeah. How would the BMO question work? Because it can't just be Bob is thinking of a number with exactly 2 distinct factors. Oh, maybe it is this. Exactly 2 distinct prime factors. And it's square free. I don't know. There's some weird ways to describe it. Good. What ones did we try? Oh, we did try. So people did try lots of one-word commands. Like, yeah, the obvious ones. That's good. Good. Worth setting those up. Maybe I should edit what to be a bit less sarcastic. I'm editing it to be less sarcastic. Okay. It could be good about it could be good. I've never taken PMO from one of here. It's just pirates. There's one really famous question from, like, I know which question you mean, and I think it was from back when I was at school that there was a pirate themed question, or maybe they've done pirate questions every year. Maybe that's just how BMO does. You sure know? I switched off follow age because I didn't understand it. You can switch it back on, and you can explain it to me if you like. This is also just James messing around with commands. Look, because if I do it, if I try and test it, it's like NA. There's no pirate question last year. Okay, shame. Pirates just make all questions better, right? Especially ones where the pirates like inherently care about prime numbers. Especially the ones where it kind of refers to historical pirate lore. I've seen some very good puzzles, not right now, but I've seen some very good puzzles about pirates sharing out their treasure, which is something they had to do. Something they had to do back in the day. Pirate crews sometimes had a kind of democracy to them. You should be able to followage now. Yeah, you should be able to display your followage. Can no one else do it? You see, it's just me, and it says NA for me. Don't get it. Oh, followage. Oh, down to the nearest minute. That's fun. Oh, there we go. That's working. Yeah, treasure sharing question in a mock interview. Right? Yeah. There's a couple of Oxford people I know who use that as a mock interview question. I won't say anything more in case it's a mock interview question you want in the future. Who's banned from followage? I do not understand followage. Also, it's just going to tell you I haven't been going for very long, so it's not like It's not like you can flex. Ooh, if you're following James for like an entire month. We've got a route to making this larger, by the way. It's not actually obvious that we can make this arbitrarily large yet. So one thing you might have spotted is that we can make this term larger just by throwing in more factors of 2. So if we look at the factors of 120, the factors of 120 sum to over 120, let's say, sum to, oh gosh, I need a different thing for this, right? Sum of the factors of 120 divided by 120 is, and then all that's going to happen is I'll get another term inside this bracket, just making this slightly larger, and I'll still have these terms for the brackets, for the factors in there with the 3s and 5s. Are some people not allowed to do followage? Oh no. Maybe it's not allowed to have too many people at once. Oh, have I put a cooldown on it? I have put a cooldown on it. Yeah, I've got a cooldown on it. Hang on. It's me. I'm the problem. It's me. I've solved the mystery. It had a 10-second cooldown on. But that doesn't make sense because it's 10 seconds. I should do the user cooldown. Different user. Yeah, okay. I'm learning Twitch. Right, good. Okay. I've set it up so that you can check how long we've been following. Anyone can do that, but only once every... I never thought being a streamer would involve this many numbers. Ish. Yeah, Neutrino got there. Chill novices. Sounds so rude. Can't we just chill? What is this going to be then? So this product is 15/16. This is so weird switching between live stream banter versus at the same time. Oh, is this going to be good? I've got a feeling this is good. There's a 15 cancelling down here. And I can see the 4 in there. Is it 3? Chat. It's not 3, is it? I've done 50, it's not 15/16. It is 15/8. Because it's 1/8 short of being 2. It is 3, isn't it? I think it's 3. I think the sum of the factors of 120 divided by 120 is exactly 3. I really want this to be true now. I think I've made some typos along the way. Yeah, no, I think it's 3. I think it's 3. That's what I wanted. Before Zoe gets too excited, this is not a proof that this is the only number that gives 3. You didn't think that, really. I'm just calling you out. Completely uncalled for as well. There might be other numbers that give us 3 as the ratio of the sum of factors to the number itself. I guess what we've discovered is putting it strongly, but I discovered is putting it strongly, but where did we start? We started by thinking about whether the sum of the factors could be equal to the number itself. No, except 1. Standard perfect numbers sum to twice the number, and we've now got an example where it sums to 3 times the number. We can make it a bit larger. I hope you can see, though, that what I want next, more than anything, is a number where the sum of the factors is exactly 4 times the number. I don't think I can get there just by throwing in extra factors of 2, because there's a limit, right? In quite a literal sense, there's a limit to this term. So there's only going to get as large as 2, and the other things are 24/15. So I'm bounded by 48/15, which is just slightly larger than this. But I could get some extra juice out of these terms by extra 3s and 5s, and there are more primes. Famously, there are loads of primes that I could be using. Level is tricky. All the best maths. So I saw the level question in chat. all the best maths has multiple levels operating at the same time. So, for example, Zoe's going to go and fine with me if you want to go and write some code. Some people are along for the ride to just watch the numbers work out. There is something going on about limits and kind of two sequences at once and multiplying different sequences together. So when two people look at the same maths, they might be seeing different things. In terms of what maths you need to have seen before, almost nothing, right? You need to know the word factors. It doesn't help if I write it like that. A factor is something that divides into a larger number exactly with no remainder. The coolest level. It's who we are, that's what we do. Good, okay. I was trying to think of a version of the river analogy there. There's this thing people say about the passage of time, right? That you can never stand in the same river twice. Because if you get in the river, you get out the river, and then you get back in again, but oh no, the water has moved on, it is now a different river. So there's maybe a version of that where the problem is I've just gone straight to the Maro flavor text, which is not a real proverb, but no two people see the same. Maro, which is not a real proverb, but is the flavor text of a Magic the Gathering card. So there you go. That's what we're trying to do here, to mess around with some maths where you might be thinking different things as it's happening. For example, you might be thinking the limit here for this geometric series is, well, for this one it's the number 2, but in general the limit of this series, if I throw in lots of extra 3s or something, the limit for what happens if I throw in loads of them is 1 over 1 minus 1 over p, which is p over p minus 1. So the kind of natural question is, well, okay, is there an upper bound? If I have lots of different primes? And congratulations, you've invented the question. Is product over p prime bounded? So is the product of p over p minus 1 bounded? Kind of might be and might not be. That's a big pi symbol, by the way. You might have met the big sigma symbol for summing. This is the big pi symbol for multiplying things together. By the way, if there were only finitely many primes, then you would... If there are only finitely many primes, this would just obviously be bounded, because it's just the product of some terms, but there's infinitely many primes. Zoe asks, have you seen the Turing complete machine you can make in Magic the Gathering game with just card interactions? Yes, and when I was at university, I was at a Magic the Gathering club with the guy who invented that. There's one person who demonstrated that Magic the Gathering is Turing complete, who hung out at the same Magic the Gathering club as me. It was cool times. Very cool guy. Also worked on board games. I don't know if any of his board games. I don't know if I can plug any of his board games. Yeah, just a sort of normal nerd hobby where you hang out with some other mathsy people, play a nerdy card game. God, I love Magic the Gathering. Right, let's not make this a Magic the Gathering stream. Story time quickly. I'm really awful at Magic the Gathering. That's the story. There we go. Okay. And when I was at uni, I ended up in a confusing series of events. I ended up in charge of the Magic the Gathering club. Super cool. This is a cool stream. There's not many positions more cool in a university than running the Magic the Gathering club. And bizarre set of circumstances where I ended up being in charge of a hobby which I was terrible at. So there you go. This is why we're not getting. This is why we're not getting a Magic the Gathering stream, because I suck at that game and am heavily invested in it. Help! I play an awful lot of Pauper. Awful lot is exaggerating. I play some Pauper. Pauper is the format where you get to play very old school Magic, but only using cards that have been, in some sense, mass printed. So that's not quite true, but it doesn't quite work like that. But in some sense, it's not playing with super scarce, unavailable cards, but still with the power level of the old days. Would recommend Pauper. Hang on a minute. Somebody 2 years above you. I've got someone out first time chat asking about Magic. I saw that. Someone 2 years above you wrote a bunch in a personal statement and got accepted to Oxford Maths. Yeah, sure. Cool. Yeah. That's not, to be clear, for legal reasons, that is not how we make admissions decisions based on whether people have the same hobbies as us. That would be very, very problematic. Look at me doing my legal disclaimers. Thanks for the follow. Who's followed me? Is this the screen? I haven't got it set up very well. Eat my mouth. Your first time in chat, I got you. All this talk of nerd hobbies. That's how you get follows on Twitch. I actually don't know the answer to this question. I mean, in the way I phrased it on the screen, I've left it on the screen for a few minutes now, and I don't actually think I know the answer straight away. I mean, I'm pretty sure it's unbounded. I think the answer is no, but I don't think it's obvious. This is a product of lots of terms, but the terms get really close to one. I suppose it could be the case that there are infinitely many primes, but the new ones are so large and they're so spaced out that each time you do this, each time you multiply in the next prime, p over p minus 1. Sorry, let me say that again. It could be the case that as you go, the primes get large so quickly that when you multiply by p over p minus 1 for your next prime, that makes very, very little difference. And overall, this thing never gets past 5 or something. I think that's not true, because the primes don't get fast. Don't get large very fast. But, what are we going to do? Sort of want to write a script for this, to be honest. Or delegate to someone better at scripts. Yeah, a cool person thinks it's a bit like a log graph. There's probably some facts about the distribution rate of primes here, right? That could come to our rescue. You might know that there isn't a formula for the nth prime as far as we know, but there are some general statistical properties that primes follow, some sort of average laws about how far apart they are and how, not quite how far apart they are, but what the density of primes is. Maybe to show you what I'm worried about, I'd like to give you some examples where this does or doesn't stay bounded. This is going to be tricky, isn't it? We're going to do this. Okay. So if everything's prime, well, okay. Let's imagine. If instead of primes, we look at all numbers, n over n minus 1. That's greater than 1. So let's go n greater than or equal to t. Then that's 2 over 1 times 3 over 2 times 4 over 3 times ... And I hope you can see that every time you put another term on, 3 over 2, 4 over 3, that kind of cancels with the previous one. And this is equal to 2, this is equal to 3, this is equal to 4, and so on. So it's not bounded. And in fact, this doesn't converge to anything sensible. It just keeps getting larger the more terms you throw in there. And maybe this gives you confidence that, if you've got this sequence where you're multiplying by things that are bigger than 1, then it will just run away to infinity. But in fact, that is not the case, because if instead of primes we look at, now here I need some sort of sequence that grows really quickly. Oh no, let's do square numbers greater than 1. I've got an idea for this. It's kind of awkward demonstrating this nicely. So this is the sum over n equals k squared. The product, sorry, of k squared over k squared minus 1. Greater than 1. So 2 squared over 2 squared minus 1, multiplied by 3 squared over 3 squared minus 1, multiplied by 4 squared over 4 squared minus 1, multiplied by 5 squared over 5 squared minus 1. What are we doing? Ooh, the chat's doing some stuff. I feel like it's a bit like a lot. No. Highest I can find less than 10,000 is 50/40, which is ratio. So Zoe in chat's pushed it to 3.84 as our current record for whether the sum of the factors could be very large. And that is 7 factorial. And then Larud says, please check 8 factorial. And that's got slightly larger. So this is what's going on in chat is probably more interesting than what's going on stream. In chat, Zoe's running some code to check what happens for n factorial. How many factors that's got. That is a complicated question, by the way. That is a complicated question. n factorial's got quite a complicated prime factorization, so I can't just get out my formula. Anyway, I was going to show you this sum because there's something cool going on with this, right? I think. There's loads of difference of two squares stuff. This is why I wanted to show you this one. This is 1 times 3 by difference of two squares. This is 3 squared to the negative 1 is 2 times 4. This is 3 times 5. This is 4 times 6, and so on. And then there's a beautiful amount of cross-cancelling. I remember this one because we've seen it before on something else, which no one's going to remember, but that's fine. So as you keep going, lots and lots of terms cancel, and this product does exist. It does work out. It works out to be exactly 2. So yeah, because one of these 2's cancels here, and the pattern is that the square on the top cancels with the previous term and the next term, cancels the previous term and the next term. And these 2's have got nowhere to cancel. There's a 1 downstairs that's got nowhere to cancel either, but that's okay. I just get the number 2. So on the board, what I'm trying to do on the board is show you that depending on which subset of the numbers you look at, this product might be unbounded, that it just keeps getting larger and larger, or it might be bounded. And the question, I suppose, if you're interested in these primes, is maybe that are the primes more like the numbers, or are they more like the square numbers? And we've got some tricky in-between cases to do. I think I might need to park this here because it's getting too tricky for me to do in an interesting way, and possibly too tricky for me to do. Neutrino says well, though, which is good. It's 50-50 whether Neutrino is interested in Zoe's calculations chat, or my claim that this horrible product, bam, is the number 2. We kind of got 2 things going on at once, which I like a lot. Are you trying larger factorials? 120 was 5 factorial. Oh my goodness. Yes, I also spotted the difference of 2 squares before I said it on stream. If it's, what's factorial's got to do with this? I genuinely don't know. If this is a fact, I genuinely don't know this. That is it true? So is the claim something like, this is based on calculations in chat, that maybe n factorial has very large sum of factors? No, that's not quite what you're saying. You're saying it's got... Can I use this sigma notation? Is that going to annoy people? I think it might be time to bring in the sigma notation thing. Oh my goodness, what am I doing? Oh, whoops. There you go. No, you saw nothing. Yeah, I think I want the sigma notation at this point. So this long phrase, sum of the factors of 120, I would like to write that as just sigma 120 for a little Greek letter sigma, which you do like this. So the claim in chat is larger than all previous values of sigma k over k. Maybe. It seems like that's where we're going. So you work out the sum of the factors, divide it by the number, and that peaks, or that hits a new high at each factorial number. Seems like the claim. 120 was pretty good here. Zoe in chat was telling me about 5040 and then 8 factorial. Not obvious if we've checked the numbers in between. So this is either true or not true, and it kind of doesn't... I love not knowing, right? Not knowing is great. There's two possibilities. Either this is true, in which case, cool, I found this like nice way to set a new record of... That's kind of like a new way to set a record of how large the product is. All things we found so far are under 4, but which is also interesting to me. They seem like they're getting very close to 4, though. Yeah, we haven't found anything yet which does the magic 4. Maybe it's true, maybe it's not true. Either one of those is interesting. That is, I think, the key of maths research. To try and work on questions, if you can, that are interesting both ways around. Which means finding the edges of your understanding, or if you're at the cutting edge of research, it means finding the questions at the edges of everyone's understanding, our collective knowledge, and trying to find the version of the question where it's interesting either way. Many years ago, when I was doing applied maths research, I got confused quite a lot, but the confusion was always because, there would be two contradictory things in my head. My understanding of one thing, my understanding of something else would contradict each other. And that's kind of really good news when that happens, because probably one of those is wrong. And the best way I can find out which one of them is wrong is sort of bash those two facts against each other, like playing conkers, or like just smashing particles together in the Hadron Collider or something. But to try and find, here's the frontier, here's the boundary where I don't know what's going on. But one way or other, one of these things is going to be false. That speech was supposed to be buying time for someone in chat to tell me this is true or false, but chat's gone real quiet. Okay. How would we test this? I would probably test this for... I would check this for a lot of numbers, but factorials get fast very quickly. Nice. Factorials get fast very quickly, so quite soon this is going to get out of the realms of where you can do straightforward calculation. At some point you're probably going to have to interact with what this sigma thing, sigma of n factorial, actually is. It's kind of one with everything, right? It's got a load of, it's got all of the primes in, right? Everything up to n, and also a whole bunch of even numbers, which makes writing down its sum of factors a bit tricky. Why would that be good? Rather than like n factorial over 2 or something. Also contains loads of primes. Why would you want that extra factor of 2? Oh, it would make it slightly better. Throwing in a factor of 2 always makes things slightly better. Better than everything else? Yeah, so what's the alternative? Up to n factorial. Oh, n factorial is huge. All previous values of sigma k over k. N factorial is really big. There's a strong claim because there's lots of things. Like if Zoe says in chat 5040, 5040. It's the best one. It's better than all previous numbers, including ones with like weird prime factors like 49. 49 is not prime. Do you ever feel like you're in somehow the wrong seat? Like you're just in the wrong place. Oh, imposter syndrome. That's what that is. Good. Right. Okay. Our quest continues. I would like several things. I would like to know, is this true? Not sure I'm going to get there today. I would like to know, is this true? But more than anything else, I would like a number where the sum of its factors is exactly 4 times the number. Okay, I'm going to work on, here's what I'm going to do. We've just gone past 3 o'clock. I'm going to do some sort of internet searching on the product of prime stuff, because if that thing is bounded, I suspect it's not, but if that thing is bounded, then we're done. Especially if it's bounded by 4, that would be really cool, because that would say, actually, Zoe in chat is calculating those things 3.9, 3.8, but 4 is the upper bound by having these primes in. It just seems unlikely that I'm going to say that, though. I'm pretty sure it's unbounded. Okay, I'm going to do some research. Talk amongst yourselves for 2 seconds while I try and find out whether the thing is bounded. Is the sum... what's it called? What's this sigma thing called? It's the... no. It's a function. Which function is it? Sigma function. Is sigma n. Sometimes just ask Google, right? If n is bounded. Asymptotic exponents. Oh my goodness. Then you find upper bound for sigma n. And then what usually happens when you Google something like this is you come across a Stack Overflow page. If people have Googled stuff before, you must have bumped into Stack Overflow. Here's a Stack Overflow page, which says, because I wanted to know this, upper bounds for sigma n. Sigma n is that sum of the factors, which would probably be, I mean, here I think that the question asker is definitely aware that this is bounded by n. Like most Stack Overflow questions, it's off topic, but I don't mind. I just came straight from Google. I don't even know which one I'm in. No, off topic because why is it off topic? It's boring. Okay, Stack Overflow reasons at the top. This thing's closed. Can I show you the full width of the thing? That'd be nice, wouldn't it? There we go. Shuffle this over here. There we go. Okay. And then you get down here some brilliant answers. I love Stack Overflow answers. They're always so confident. They're always so complicated. Why is there a Riemann hypothesis halfway down this post, right? It's a very short post with the Riemann hypothesis in it. Okay, from Robin. Okay, citation, I suppose. For n bigger than or equal to 13, here's a bound. E to the gamma, log n. It's the most maths thing I've ever seen. Constant over log n. It's got all these logs and e's. Isn't this brilliant? The easiest sequence of numbers. Almost 1 of this thing divided by n e to the gamma log n. Easiest sequence of numbers. What are they telling me to do? I'll take the lowest common multiple. This is like Zoe's factorial, but getting rid of extra factors. The very best values come from the sequence of colossally abundant numbers. That's Okay, so this is what I love about looking up things on Stack Overflow. You come in with one question, and you get like 10 more questions of reading something written by someone more clever than yourself, right? Yeah, I'm pretty sure gamma is in this sort of maths, gamma is usually the Euler-Mascheroni constant. We can check, I suppose, because I know what E is, and that looks like it's about the square root of E. Yeah, that looks like it's about the square root of E. Gamma's about 0.5 if it really is the Euler-Mascheroni paper. Paper in English by Briggs as theorem 1.1. Cool. I would not have guessed that it's this weird. And this Stack Overflow person suggests doing an experiment just like the one Zoe's doing with, this is the lowest common multiple, but hey, why not factorial or something? And answers this question about when it's the best, apparently, in terms of colossally abundant, which I've never heard of and has capital letters, so it must be important. And then, out of nowhere, claimed that the Riemann hypothesis is equivalent to the statement that for n bigger than or equal to 5041, one of the numbers that Zoe was checking before, that number could be replaced by 0. Oh, so you could just have this term. After a while, even better. And that's equivalent to the Riemann hypothesis, apparently. The average stack exchange experience and the average maths is beautiful formula. Well, no, this is maths is beautiful, right? Because this is hideous, but apparently the Riemann hypothesis says that if that's true, if the Riemann hypothesis is true, then we can do a slightly better version, which deletes this term. So it just says more research required, right? If we prove the Riemann hypothesis, we can cross out some terms from this thing. First up, Zomogosh is a fantastic domain name. Second, am I supposed to click just unsecured links? Yeah, this is a collaborative stream now. Let's put it in the one that's not live first. Whoa, yeah, cool, great. This is just the sort of website that I thought people watching this stream would make. Oh, I love this, brilliant. Right, okay, so I can put in 5040 up here. And then this will find excellent stuff. You haven't even typed your umlauts. You got to type your dots. Oh, that was quick. I don't know why I thought that would be slow. There you go. You're now on a Chill Maths live stream. Everyone, hang tight. Oh, very close to 1. Possibly prime. This is great. Oh, this is brilliant. Excellent stuff. I'm enjoying this a lot. Nobody told me about 720 in chat. Yeah, can you tell me the best number up to 721? It was 720. Oh, it looks so factorially. But what are the colossally abundant numbers that Stack Overflow person was talking about? Also, I suppose they were talking about the ratio of n. If it was true that that thing was just bounded by 4, then I think they would have said that instead. This is not quite how maths works, right? But if it was true that the right-hand side was, if this thing that I'm interested in was just bounded by 4, then probably they wouldn't write out all of this stuff. They would write 4. That would be a better Stack Overflow answer. It's sort of annoying that that's not quite how maths works, but it is kind of how human communication works, and Stack Overflow is kind of in between. Embarrassingly, I don't know any more factorial numbers off by heart. Is that embarrassing? Yeah, I think it is on this stream. Ooh. That not 8 factorial. Oh, and it's 4. You beat 4. It's not exactly 4, but we beat 4. 362880. A lot of the people in chat on this. Is n factorial plus 1 always prime? Ah, now I get to do some maths. Now I get to do some maths. I'm back in. Cool, let's switch here. Let me teach you Wilson's theorem. Wilson's theorem says that p factorial is, let me get this right, 1 less than a multiple of p. For example, 120, which is 5 factorial. No, this is nonsense. Ignore me. Ignore me. Ignore me, ignore me, ignore me. P minus 1 factorial? Wilson's theorem, to the internet. Let me teach you Wilson's theorem. But first, let me learn Wilson's theorem really fast. Am I going to get all the minus ones right? Oh, come on. I don't like this. Okay, p minus 1 factorial. Good. It's 1 less than a multiple of p. Yeah, the first thing I wrote down was stupid. And I'm not actually broadcasting this, am I? I'm just showing you. I'm writing but not showing. Somehow. Good times. Oh, have I clicked there? No. Twitch is hard, chat. Twitch is really difficult. I have approximately 60 things open at once. Yeah, so I agree. Okay, let's catch up with chat very quickly. Are the numbers 1 and above and 1 below each factorial always close to 1? Kind of. I mean, everything's a bit close to 1, isn't it? I know this fact about factorials though, which I want to try and do. Here we are. It's happening. Don't use 5 factorial as your example. 5 factorial is not p minus 1. I can do this. For example, 4 factorial is 24 is 1 less than a multiple of 5. So I think somebody in chat at one point just now said, if you take n factorial and add on 1, do you always get a prime? And the answer is no. Or 6 factorial is 720 is 1 less than a multiple. That's multiple of 7. If you're looking at p minus 1 factorial, 10 factorial is 1 less than a multiple of 11. And that means that these things will have some non-trivial factors when you add on 1. So on Zoe's calculator, I was trying out numbers like 721, which is quite close to 1, but not very close. It's got this extra factor of 1 plus 1 over 7. So it's a little bit bigger than 8 sevenths. Yeah, a little bit bigger than 8 sevenths. So you can prove it's not that close to 1. I don't know about this. That's very close to 1. That looks suspiciously prime. It's sort of almost a way of detecting if something's prime. It's a stupid way of detecting if something's prime, but my way of checking if something's prime is to put it into this website and see whether or not it comes out extremely close to 1, because I know the primes give you something close to 1. Bottom one is prone to crashing. 332640. Is that another factorial number? I really think we're on something with these factorials. This is great. Exploring along the way. Right, yeah, it's the difference between being prime and being coprime with a bunch of stuff. So, well, obviously 10 factorial is not a multiple of 3, 5, or... Sorry, obviously 10 factorial is a multiple of 3, 5, 7 and stuff. So if you add 1, then it won't be a multiple of 3, 5, or 7. But 11 is like the next prime up, which we should check. What am I doing? Sorry, I really thought I'd regained control of the narrative a bit by remembering Wilson's theorem, but then it turned out I didn't remember Wilson's theorem either. We're having fun. We're doing all sorts of things. I should go back and look at that number theory page. Good. Okay, the other thing I wanted to look up when I saw this was colossally abundant numbers, because there's this claim on Stack Overflow display. Let's quote Will. Thank you, Will. Oh gosh, no, don't do this. Oh, this is the thing I wanted. The product for primes up to k. Prime number theorem, yeah. I was worried it would be this. The grown-up thing would be to teach you the prime number theorem. So we will learn the prime number theorem and understand how that bounds the thing, but that's just so boring. That's just so boring. I think the fun thing to do would be to just look at more crazy maths. So I kind of want to find out about colossally abundant numbers. Oh, are they abundant in the sense that they've got their factors summed to a large number? That would be cool. Oh, simple Wikipedia has a page for this. Oh my goodness. This is the Wikipedia page we've been looking for. It's so hard to find Wikipedia pages sometimes, because sometimes you just have to know what you're looking for. There are some spikes on this graph in terms of large compared to n. Look at that graph. The colossally abundant number is a natural number, has many divisors. Ratio between the sum of the integer divisors, thing we've been doing, and that integer, oh gosh, raised to a power higher than 1. Oh no. For any such exponent, okay, great. Can I have 0? No? You compare it to all other numbers? Oh my goodness. Also, the first 15 superior highly composite numbers. Oh my goodness, and they are, well, this sequence includes some factorial numbers, but skips others. And the definition is slightly different because of these epsilons. Maybe this is not the Wikipedia page we were looking for. But there's another e to the gamma n log n. If you wanted to see that factor on Wikipedia rather than on Stack Overflow, with actually this time confirmation that gamma is the Euler-Mascheroni constant. Do people know about this, by the way? I think it's neat. It's the difference between what you get when you integrate 1 over x versus what you get when you sum 1 over n. And those things are pretty similar because of areas under a graph. If you integrate 1 over x from 1 upwards, then you get this purple area. And if you sum 1 over n, then you get something slightly different. You get these rectangles, and the rectangles kind of are above the purple curve. Can I look at this picture? There we go. The Euler-Mascheroni constant is the sum of the areas of this top bit, which perhaps surprisingly converges. It's a number. It's about 0.5, 577. I don't know any digits of this one. We don't know very much about it. We don't know if it's irrational. It's definitely irrational. It's just obviously irrational. Oh, what happened there? Oh, a little map of Switzerland. Wikipedia is lovely, isn't it? Sometimes shows you Switzerland. Converge, yeah. Good, okay. Let's go back to this page of claims. I didn't prove Wilson's theorem. I think it was bad enough that I couldn't quite remember Wilson's theorem. This I'm going to go maybe, but I'm getting a little bit nervous. Maybe, maybe not, but maybe understanding that would be a good thing to do before we try and understand colossally abundant numbers. This one I'm going to go, no, looks like it grows like log n or something due to the prime number theorem. Out my depth. What are we clipping? You can clip things, I think. Oh, does 27720 do slightly better? Fact check. Back to one more look at the page. We're doing this scary thing where I'm just broadcasting my screen, which you're not really supposed to do. Anything could happen. What is that? I have no idea what just happened. It's big. Oh, you've redeemed a thing. You've redeemed a thing. What does it say? It says hydrate. It's a reminder to drink water. It applies to everyone. Thanks. Yeah. Thanks for the reminder. You earn channel points just by being on the stream, and at the moment, the only thing you can do with them is A, highlight a message, which makes it louder, or B, remind everyone in the stream to drink water. Counts you as well. Right, good. Okay. Do I need to set a cooldown on the water? How bad is this going to go? I'm not quite sure what rate you earn points at. Yes, this is annoying. It's the claim that this is 8 factorial. Okay. Good website. Like it a lot. Small chance of getting cancelled. I enjoyed that a lot. Thank you for building a website during a live stream for some idiot to include on a live stream. Great. Remember, this is the stream where we do some maths and we try and learn some maths. And for me, that involves, I think now, an answer up here. No. Sad face. But it's not about the end point. It's about the journey along the way. I mean, seriously, it sounds cheesy, but along the way we tried out some stuff with. We almost discovered colossally abundant numbers, except I don't want to look. I want to look those up again afterwards. I think I can't even spell them. Colossally abundant numbers had like a complicated definition with some epsilons in. Right, half an hour, and I want to do the thing that I was going to do. We still haven't hit exactly 4. Really distracted. I feel like this is the sort of thing that people must have thought about before, right? If it's unbounded, it goes past every number. Does it actually hit every number? Is there a number out there? We've seen on Zoe's website that it gives these kind of like complicated rational numbers for the ratio. But 120 was sort of cute. 120 actually hit the number 3. Can we find a number that hits 4? I have no idea if that's possible or how difficult it is, but that is, I think, currently homework. So let's go homework. In inverted commas, just to make it clear that it's not really homework. Well, you did say, hang on, proof by exhaustion, but you did prove it. You proved it in the negative. You proved it was not true by just finding a counterexample. That would be really hard. Really hard with pencil and paper. And such that sum of factors is 4n. I'm not certain that's a good idea. I think that might be a bad idea. Understand colossally abundant numbers. That's more for me, I think. I was interested in those and I want to learn more. And Wilson's theorem. But I want to go back to that kind of exploring we were doing at the start, where I think, oh gosh, ages ago, somebody said we should do a power of 2 multiplied by something else. I think you wanted a power of 3 in here, but I'm just going to put one prime in. I've gone for Q because I'm thinking of PQ again. And K for a power? I don't know. There are some perfect numbers of this form. I know because 6 and 28 are numbers of this form. There's something nice going on where the sum of the factors here is 1 plus 2 plus 2 squared. Once again, we've got quite good at this calculation now, I think. I don't know if Zoe's code factorizes the number and then uses this factorized form, or whether Zoe's code searches for all factors and adds them. Either would be okay, but we've got quite good at this now, haven't we? So I'm going to try and do it like this. So here's the kind of cool observation. If, and it's quite a big if 2 to the k plus 1 minus 1 equals q, then, I mean, obviously that first bracket is q, and even better, the second bracket is 2 to the k plus 1. You see, they sort of both do something. This one becomes q, and this one becomes 2 to the k plus 1, which is exactly 2 times 2 to the k times q. So then 2 to the k q is perfect. It's a perfect number, sorry. Oh, all we need is 2 to the k minus 1 to be prime. And then we work out 2 to the k, oh, do I want that? 2 to the k plus 1. 2 to the k plus 1 minus 1 multiplied by 2 to the k. You've done a big search and found multiple 4s. I missed that in chat. Good stuff. Maybe I need to just turn on something which makes it make a ping noise for me. I don't want it to make a ping noise for you, but maybe can I make chat make a noise? Something for next week. Had a quick look. Can't see anything obvious. What's a request queue? Whoa, it's opened a thing over there. To get rid of that. Oh, it's a hydrate, right? I gotta mark it as complete. Cool. Okay. Sorry, I've got to tell Larue that I actually did it after I did it. And it opens a Twitch panel, which was terrifying. Don't broadcast your screen on Twitch. Always use window capture. If window capture's broken, I don't know, do whatever. Yeah, I quite like the idea of chat noises being really, really obnoxious. I like it being the idea that it's like a ping or something that's just really, really annoying. Oh, I suppose the microphone would then pick it up again, probably. So that would be maybe quite annoying. Maybe I don't want to do this. Okay. I like the way this turns out to just be a triangular number. These are currently... So ones where 2 to the k plus 1 minus 1 is prime are currently all the ones we know. I have to put currently in. At time of recording, all the perfect numbers we know. All the ones we know fit into this formula. We don't know if there are any others. So this is kind of silly. It means we don't have a formula for perfect numbers, but we have this kind of almost a formula, which doesn't always work because it requires this thing to be prime. It doesn't always work and it might miss some of them, which is stupid because literally any formula you could say both of those things. It doesn't always work and it might miss some. Between them, those add up to nothing. And yet also it's probably right. Really feels like this. We know this is a we as in all humans on Earth. Maybe the dolphins on Earth know some more perfect numbers, but they haven't told us. And I suppose it's all humans. Is there a chance there's a human out there who knows an odd perfect number but isn't telling? Yeah, maybe it is. Good, okay. Got to specify, right? All the humans, all the talkative humans know. Anybody who'd like to be famous? Astronauts! The astronauts! On or near... we don't think the astronauts found any perfect numbers up there. Now, I made a sort of slip of the tongue mistake there, in that I immediately switched to talking about, well, the alternative would be an odd perfect number. And that's not actually obvious that the alternative to this would be an odd perfect number. This is an even number, but there's other even numbers, right? Like struggles to think of an even number. 120 is an example of a number that doesn't fit into this pattern, but isn't odd. Yay! I would sort of get it if somebody came out in their will. Maybe it just says, by the way, 35 is a perfect number. Can't believe you all missed this. You've got to respect the hustle, right? Just hanging around, going shopping, coming home, like, I know an old perfect number. Right, anyway, let me show you the page that I thought we were going to be looking at today, which is the one with a proof that all of the even perfect numbers are of this form. I hope you agree that's a kind of point I should make. You could sort all of the perfect numbers in the world into even numbers and odd numbers. Within the even numbers, some of them are of this format. Within the odd numbers, we don't know. Have we checked 35? I think you have. You wrote some codes to check 35, right? Your code checked all the numbers, right? We have checked 35, because 35 is the product of two distinct primes, 5 and 7. And the only perfect number that's the product of two distinct primes is 6. That's the Nexenator theorem. I don't know if you set that up, but... good times. Right, what am I doing? I'm going to show you the even number thing. I've completely lost it. I'm going to find it again. I mean, I've lost the page, not lost the plot. Maybe I've also lost the plot. This is a cool website. Well, I think it's a cool website that I've never seen before. Which maybe I should hang out on more. It's got loads of just stuff about prime numbers. It feels very relevant right now to what we're up to. Maybe I should just try exploring this page at some point. Not live, James, not live. If you've been here for the last hour and a half, I showed you this page about an hour and a half ago because I thought I was going to be doing. So here's the theorem. It works both ways, this theorem. If this thing is a prime, then that's a perfect number. We just did that. And every even perfect number has this form. That's quite a big claim. That says that if you're searching for perfect numbers, don't bother checking 120, 122, 124 or something. You only have to check these very... these numbers are very sparse. They're very spaced out. There's not very many to check. If you want to check up to 1,000, there's not very many of these numbers before you get to 1,000. There's a good speed up if you want to check. So I'm very interested in this and bit, right? And every even number, perfect number has this form. Right, good, okay. The proof is quite short, and I'm hoping we can look at it in the next 17 minutes. Which sounds weird when you say it out loud. So first, they've got this calculation, and they've done it a slightly different way, but you know, it looks fine to me. Here are the terms: the p plus 1 bit and the 2 to the k minus 1 bit. They've got different k minus 1 instead of k and k instead of k plus 1 compared to what I did on the screen a minute ago, but this is the same maths. I'm to show that n's a perfect number. They're making heavy use of this sigma notation, which means the sum of all of the factors of a number. Okay, so I think this is the bit I care about. Can I get it all on screen at once? That'd be cool. Zoom out a tiny bit. There we go. Okay. My job now is to try and understand everything that's on the screen. No scrolling. 15 minutes, me versus maths. If you're just joining the live stream, this is a kind of a learning experience that's now also rapidly becoming a speedrun, where I try and understand some mathematics and also try and bring chat along with me. If you're watching, let's see if we can understand this. Okay, on the other hand, suppose n is any even perfect number. And write n as, what's this? This says pull out all the factors of 2 where m is an odd integer. And you're going to call that 2 to the k minus 1. Fine, okay, I guess. Where k is bigger than or equal to 2. Because the number of 2's in there, you have to have at least 1 2 to make an even number. Suppose n is any even, blah, blah, blah. You have to have at least 1 2 in there. And yeah, cool. You can have a load of 2's if you want a load of 2's. And then m in here is any odd integer. I suppose we're trying to prove that this is a prime. We're trying to prove that that's a particular prime, 2 to the k minus 1. It's going to be very hard to read this sort of thing out because there's a lot of 2 to the k minus 1s and also 2 to the k minus 1s, which I cannot distinguish out loud except by pausing, and this is a speed run. Doesn't 28 have a square divisor? 28's got a divisor of 4, right? Trino was here. Okay, here we go. Sigma is multiplicative. I think that means, in this context, that means that, okay, the sum of your factors, think about how many 2's you're throwing in there, and then this m doesn't have any more 2's in. So it's made of other primes, so those terms come up separately. It's sort of all multiplied together. I think that's all that's going on here. So we know the 2 bit, and then we know also you've got some 3's you've got some 17's, whatever. All multiplies together nicely. Those brackets that we've been looking at for the separate prime factors. Since n is perfect, this is supposed to be 2n, which is 2 to the k m, which is looking like it's pretty close to this, which is going to force sigma of m to be quite small. So these things are supposed to be equal. Now, 2 to the k minus 1, what is this? Divides, oh yeah, okay, so this left-hand side is a multiple of this. They're just going to say this looks very suspicious. Hence, 2 to the k minus 1, which is very much not, okay, so this thing is it's not even, so it can't be a factor of, it must be part of the m part of this number. We found a different way to factorize this number. We factorized it like this, which is a bit suspicious because it's got a big odd number in it. That's going to be a factor of m, not of the 2 to the k's. So that divides m. And then, okay, because it divides m, we can write it as some multiple of 2 to the k minus 1. Okay, so this m over here is some multiple of this number here. Pretty good. Substitute it back in and we get 2 to the k big M is sigma of m. Right, okay, so we're getting somewhere because now we've killed off a prefactor and we've got a fact about sigma of small m. Small m was this number up here for the remaining factor. We're trying to prove that it's a particular prime. Okay, since little m and big M are both, the other thing I can't distinguish out loud is the lowercase m's and the uppercase m's, but this is a speed run. They're both divisors of smaller case m. Yes, they are. This one obviously is. That one is in there too. Thanks for the follow. We know that, oh my goodness. So this large number, which is sigma of m, because of the division we've done, keep it together. We did some division. We got down to this fact. So 2 to the k big M is sigma of small m, which must be at least as large as, yeah, okay, here we go. This inequality is key. This is going to be where the magic happens. The magic here is that small m could have loads of factors in general. We're trying to prove that it's a prime number, I think. What are we saying? We're saying that it's got a factor of at least itself plus, now this suspicious, large m. Why is that? I'm worried that might be equal to small m. Why is that not equal to small m? Oh, because it's definitely not equal because this thing is not 1. Because k is bigger than or equal to 2. So this is bigger than or equal to 3. So this is genuinely some non-trivial multiple of big M. So these things are actually different. Okay, I'm a little bit confused about where we're going. I thought I had a direction, but don't quite have a direction. Anyway, we're still in this. And what's this thing on the right-hand side? Where was I? I was at the factors of small m have to include these terms, plus maybe some other stuff. But that is equal to, why is that this? Oh my goodness, because small m was actually this. Ah, right, which is the idea. That's the idea that this small m, modulo some stuff, the small m thing up here, no, it's the idea that's very close to being 2 to the k m. We've taken that term and added on one more m to get to 2 to the k m. This is a classic maths thing I've seen where you start with something on the left, there's an inequality in the middle, and then you get back to the same place. which proves that the inequality is actually an equality. The only way for like x to be bigger than or equal to something is for those things to be... These things are, on the one hand, both equal to this number, so they're equal to each other. That sounds stupid, but there you go. These things are both equal to 2 to the km, so they're both equal to each other. Yeah. Yeah. The sigma over is m plus big M. I don't know, hang on, I'm now not sure this inequality is doing anything. Could this just be the word and? This could just be the word and, I think. Anyway, this means that m is prime. Oh no, I've lost it. This means that m is prime. Oh no. Focus. This means that within number theory we're in prime numbers, I would say. We're trying to understand factors and perfect numbers. It's a speed run. This means that m is prime. That's thrown me. Only 2 divisors. Is big M a prime number? No, that'd be daft. Well, big M is 1. Oh, we said that, hang on, so this is factors. These are factors of small m. If it had any more factors, they would make the sum on the right-hand side bigger. So what we're saying is this is all of the factors of small m. We found them all. So it must be little m plus 1. Little m plus... Its factors are now... Can we have some more factors? No, these are all the factors. And we haven't listed 1 yet. So, cool, okay, that's the number 1. So... That means that this thing, which was already defined to be, oh gosh, that means that in here this is number 1, in here this is number 1, so this is, I guess m plus big plus 1, yeah, m plus 1 in here, and this is 1, so m is 2 to the k minus 1, follow some algebra through for the consequences of this being the number 1. Is a prime number. It doesn't have very many factors, and we have proved that the number n has the prescribed form. M and its prime. Okay, we've got down to this 2 to the k, which is what we wanted, and a prime. Good. Okay. Hi, Toast Potatoes. Same time every week. Ooh. List. Link for the website that I'm currently on is this page. I should have put that in chat ages ago. Okay, I got down to the bottom, but I wouldn't say I understand it yet. So my challenge is to now try and read it again. The challenge is always to do these things. The sequence that I've come up with really is fast, slow, fast. Read it slow, read it fast. That was the fast one. Really, I've run out of time, really. But really, I should just slow read through now, trying to understand what's important. And then a fast one again. Because the live stream revolves around me doing stupid things, I'm going to try and read it fast again. Okay, so the proof works like this. We're trying to prove that any even perfect number has a very particular form. Even numbers already means you can pull out the factors of 2. To be left with some odd leftover bit, we're going to prove that that's an odd prime number. Here's how. We'll write out all the factors, and that's obviously when you write out the factors, you get something pretty nice from the powers of 2 bit. Plus, multiplied by whatever you get for this leftover odd number, which might be prime and might not be. Now, the left-hand side, the sum of factors is supposed to be exactly twice the number, which is extraordinarily similar in terms of an expression to the thing that we already had. These things look just so similar. In particular, if this thing turns out to be m plus 1, then we're good. That's just... Oof. No, we're not. Don't like it. Oh, I don't like that. M maybe not prime. No, M is going to turn out to be prime. If M's a prime, it's going to be a very particular prime. A very particular prime. a very particular prime, the ones that we want in the calculation for the other bit. Oh, yes, someone do the math. Very particular prime. Okay, carrying on. Together, these things give the number. Look, here's the relationship. Factors of this odd bit, but not too much of it. Not too much of that, please. Because if you make the number m too interesting, then it'll have lots of factors, and the right-hand side will be too large. It'll be too big, too confusing. So we've written it like this. Oh, okay, so this thing divides m. Now, in fact, that's actually equal to m, but there's a little bit of work left over. We can't just write down that this term is equal to m and sigma of m is equal to this. It could be true, but there could be some extra factor in there, some capital M factor for how much this divides little m and how much this divides sigma m. Sigma m looks very even. Oh no, it's even number multiplied by m, which is then any even number, not just a power of 2. Sub back. Oh, hello, toast potatoes. His girlfriend. Yes. Life drum is too slow. I thought it was going really fast. I know what you mean. Okay, once again, substitute back into the equation above, divide by that to get this, where I'm pretty sure this turns out to be the number 1 later on. You see, when you read it the second time, you kind of know where they're going, so you can see what's coming up. This is my way of reading maths. I'm not sure it's the best way of reading maths, but this is how I try and learn things. First time through, really greedy, just try and get through, oh my goodness, so much maths. And then the second time through, vague understanding of where it's going. It's really only by about the third read through that I think I actually know what I'm reading. People who tuned in for the quest for the quintic will have seen basically an entire week of me trying to do this on other content. We've now got a situation down here, sorry, back in the maths, where the number lowercase m has got a couple of factors. I don't want it to have too many factors. It's got too many factors. Things just be too large, right? Yeah, okay. Let's chill out then. So, oh gosh, m is this thing here is a multiple of that. My goodness. A multiple of that? That would mean, can I do a version of this proof where I pipe it back into itself, right? A multiple of that would mean that it has loads of factors. But that's suspicious. Because if it has loads of factors, then the right-hand side gets larger again. There's probably a version of the argument you can do like that. Might even be just sort of end up being the algebra is the same, but the wording is stupid. This thing. So if it's got too many factors, then this sum will be the sum of its factors will be too large. So the right hand side can't be too large because it goes into the left hand side. There's this factor of m. Yeah, okay. This bit's even. This bit's odd. This bit's even. This bit's odd. They match up to some factor, which is being called big M. I would have preferred. The way I'm thinking about it, I prefer any other letter. A good trick that I've learned is to rewrite some mathematics using different letters. It forces you to concentrate on what's going on. And I think this is the 2 different uses of that scale factor. Let me show you, sorry. So scale factor in the sense that, what have we got? We've got 2 to the k m is 2 to the k minus 1. Sigma of m. So I'm thinking this is a scale factor like this, that we have something like m over 2 to the k minus 1. That's a whole number. And so is that. All of the 2's must be factors of sigma m, because then sure as anything not factors of this, so the thing's going to have loads of factors of 2 in it. And I think these are both being called big M in the web page that I'm reading. But I think you can go through and say something like, yeah. So then maybe make the argument look like that, and then say that these things can't balance out. How did it follow that 2 to the k minus 1 divides 2 to the k m? Yeah, so, well, this thing's a whole number. we've got this weird equation. I can't quite remember where it came from. I think from writing out the factors, which has got 2 to the k m on the left and 2 to the k minus 1 on the right. So this thing, is, as it's written out, is kind of literally 2 to the k minus 1 times something else. So 2 to the k minus 1 has got to be a factor of this thing. And in fact, because this is very even and only has 2's in its prime factorisation, and this doesn't have any 2's in its prime factorisation, they're kind of co-prime, so it must divide m instead. Oh, too much number theory, too fast. Right, good, okay. Substitute back in, divide by 2k. There's a really good step here. I suppose one of the kind of silly things about this is that this was proposed hundreds of years before it was proved. That this took actual mathematicians like Euler hundreds of years to, working together I suppose, hundreds of years to invent. And there's something slightly daft about trying to understand it in 15 minutes. I think we've got an idea. You can sort of chase through the factors of 2 and make it make sense. Pacey, I don't know why I've accelerated. I had one more thing to mention just before as a kind of follow-up. There's this lovely proof out there that if I love this so much. It's so daft. So this is Googleable in the sense that you could go and look this factor up. But I encourage you to mess around with it a little bit first. It says, if you have an odd perfect number, then it is not a multiple of 105. It's kind of the perfect maths for me in that it's daft, it's got a random large number in it, just like a good old number file video back in the old days. A 105, by the way, just to give you some sense of where 105 comes from, is you'll have noticed it's a multiple of 5. It's 5 times 21, and then 21, you know, is 3 times 7, so 3 times 5 times 7. This is really a statement about what its factors would be. If n is not an odd perfect number, then it is not a multiple of 2. So 105 is not totally random, it's a bit random. There is a proof out there. I've looked this up before. There's a good somebody, a university, I can't remember which one, used this as a problem of the month or something, and also wrote up a nice tidy proof of why this is true. It is very random. The opposite would be really good. If it was true that if n is an odd perfect number, then it is a multiple of 105. That would be good, because that would save us loads of work checking numbers, I imagine. But no. There's a throwaway comment on Wikipedia that says that if there is an odd perfect number, then it is very large and it has a lot of factors. Which makes me think someone's checked numbers of the form PQR, numbers of the form PQRC or something. Like the Nextinator theorem of checking a number with just 2 distinct prime factors or something. Yes, unfortunately, putting it lightly, ruling out the multiples of 105 was not exactly great progress on the infinitely large problem of checking odd numbers for being perfect. Loosely speaking, if you don't have those 2's in there, then you have to. Your task is to do stuff like this. So you might have some 3's, you might have some 5's. To sort of make this, and you need this to be exactly 2. And what this theorem says is that you're trying your hardest to make this be the number 2. But if you have a factor of 3, and you have a factor of 5, and you have a factor of 7, and maybe some more stuff, and maybe some more stuff in here because you've overcommitted to these factors, then this, with some more maths, this can't be the number 2. which maybe doesn't look that mad. I mean, when you write it out like that, it doesn't look like the number 2. But there again, it didn't look like the number 3 earlier when we showed that 120 was exactly 3 perfect. We need a phrase for that. Cool. Right, I think I'm going to stop in a mo. It's been a cool live stream. I was half planning to run some ad breaks. I don't know. Did you have to watch an advert when you joined? I think there's ad breaks now. If you had to watch an advert, then you're supporting charity. Thank you. Also, I should try and schedule those because I think it just shows you mid-roll stuff just at the beginning. You watched an advert, okay. No ads, but there were last week. Okay, I do not understand the monetization on this platform. Something I can do is, you're a subscriber, or maybe you don't have to watch ads if you're a subscriber, because you're already using you subscribed. There you go. If you have Amazon Prime and you haven't used your free Prime subscription, there are other channels you could use it on. If you use it on this one, go to charity. See, some people, I think Twitch gives you the option to spend money to subscribe. But if you have Amazon Prime, then little known fact, Amazon owns Twitch. So if you have Amazon Prime, you get 1 free subscription a month, which you can use on any Twitch channel you like. Or you could use it here. Thank you for the subscribe, Neutrino. This call to action actually worked. If you want to not see ads, well, LaRue tells me you don't see ads. Channel points work like that. Thank you, see you. You earn channel points for just watching. I don't think you can cash them in for very much at the moment. I'm working on it. If you subscribe with either Cash Money, which terrifies me, or Amazon Prime, give me Jeff Bezos's money to give to charity. Okay, so it's something like maybe I don't need to schedule ad breaks. There's a button on my Twitch thing, which is like ad break, which maybe I just shouldn't click it. Sorry, I'm just giggling at Zoe's cardinality points. Right, ad breaks. Okay, good. Today, I like doing this. 6 is only perfect number of the form PQ, so 35 is out. That's probably the best progress we've made on odd perfect numbers. N factorial is quite... No, let's do not the n factorial thing. Let's do... Today we learned that sum of factors can be exactly 3. We had a quick look at proof that even perfect numbers are all of a particular form. I forgot to say Mersenne prime. I should probably have said Mersenne prime quite a few times. And OSD4 of these. We learned maybe don't broadcast your screen on Twitch. If you saw anything weird, no, you didn't. Right. I say so. Next Nater's second theorem, I'm concerned about, because we say it has square factors. I'm worried about like 28, which has a square factor of 4, right? Unless you're saying it's not a square number. Square factors means maybe more things. Emote related to pi as a pi. Oh yeah, then you could redeem it. So if you do channel points, I can't really see how quickly you earn channel points, because I think it's about 10 every half an hour or something. I don't really understand. You can get emotes. Cookie Monster's used an emote. Only one without a square factor. Including the odd ones. Okay, next Nater's second theorem. Something more plausible. No square factor. Oh, no square factors. All the even ones definitely do, because of that big big power of 2 on the front. That means they've got 4 as a factor. Are you saying that? Oh, are you saying that PQRST alt prime? So it's not perfect. Oh. Oh yeah, 6 is so your theorem is now 6 is the only square free prime. Yeah, well, what about the odd ones though? I think this is Nextinator's second theorem is a theorem about odd perfect numbers, which would be cool. I've put a stupid theorem about odd perfect numbers on the board. There's a chance that there are none of them, so if somebody proves there are none of them, which feels likely, but if somebody proves there are none of them, then all of our theorems are a bit daft, right? This one is just, if there are no odd perfect numbers, this one's just true because the empty set, nothing in this set is a multiple of 105. Yeah, that's not true. I don't know if it's conjecture, but ratio 4, okay. Turns out computers are good. Computers are good, but not mine. Mine is very badly behaved today. Thank you for not making me do my job during this stream as well. On some level, I've had an absolutely awful week. I've had a really bad week. It's been very nice talking about something perfect instead of the not perfect world. That was cheesy. That's what I'm like. Right, good. Okay, I'm going to call it there. Thanks for watching. Thanks for doing some maths. I'm going to recommend a Twitch channel. Oh, yeah. Let's recommend a Twitch channel. It's somebody I saw on Twitch who does maths. I just think it'd be fun. I don't think they're live now, so I don't think we can blimey. I don't think we can raid them. Sorry, it's so good I'm not showing my screen. I just went to the homepage of Twitch to try and find some maths live streamers. Wow, Twitch, that content is not okay, Twitch. Blimey. Right, okay, let's try and find... what was your name? I can't find you. Where have you gone? No. Okay, I can't find them. I will shout them out next time once I've learned what their name was. Now I've just looked at the homepage of Twitch for no reason. That's really unsettled me. I complimented your t-shirt once. That makes me sound weird. That makes me sound weird. Because of this thing where I can't see you, but like, oh, a t-shirt. I reckon you maybe came to an open day or something wearing a maths t-shirt. That's what I'm going to interpret that as. Sometimes people come to events or something wearing nerdy maths t-shirts ready to meet other maths people, and I try to compliment the nerdy maths t-shirts when I can. Right, good. Okay, things will get better. Well, you have a photo. I guess those photos. That's the problem of saying yes to people. Somebody stopped me in the street yesterday. That was a thing. I was minding my own business. I was outside. Somebody stopped me in the street to ask if I was Dr. James Monroe. That was great. It's so weird that I've met these people. You had a cool t-shirt of Problem Solving Matters. I mean, in some sense, it's not weird that I've met these people. It's just... yeah, it's just odd that some of the people I've met are also anonymous people in chat. You're celebrities, because I've met you before. Right, okay. It's a good t-shirt. It's a good t-shirt. Wait, are you all just... ah, you're at Durham. Yeah, so the one at Oxford. I popped into the Oxford one a couple of times. I try not to because Problem Solving Matters is all about people getting ready for the mat and Tamua and step. So it's not all about maths, but some people are there to try and get better at maths. And if I'm wandering around being in charge of setting and marking map. It's just a weird energy. Obviously, seeing people at other things. See, you like the Problem Solving Madness booklets. They're quite comprehensive, aren't they? There are a lot of questions in. They get longer each year. More and more stuff added in. Written by, I think mostly written by one or two people at the MEI. Yeah, I can't imagine me getting recognised either. I mean, I look like this. How are you going to spot me? It's like, where's Wally, right? Just me in the crowd. You know, it's no chance. Generic white man. It's just if you ask someone in the street, "Are you Jason Wright?" It's just like, no, I'm just some other random white man. Yeah, they put on their own live show about the mats, which is a thing, I guess. This is it. The other weird thing about Problem Solving Matters is we work really closely with them. We host the event. We help find mentors for it, and sometimes it just completely clashes with other stuff that I'm doing. Which, I mean, it's everybody's fault when you have a stream clash. But also, there's not very many math streams. It feels like we could have coordinated to not do them at the same time. And mine is always Thursdays. Oh, I did my chaos talk at. This is now slightly people. This is like. It's not doxing. Doxing would be if you posted your address. Don't post your address in chat. But I do find it humorous when people are like, "You met me at this occasion, and I saw you at that occasion." And then what am I supposed to like? I remember there were 30 faces in the crowd that day, and 400 the other time. And I'm enjoying the clues. Right. Thursday evenings. Also, you're right outside. Almost. Streaming errors. What I almost did there was point my camera at the window to show, oh no! But of course, then that would be doxing myself, because if I've learned anything from the internet recently, it's that you're all really good at Google Street View, or at least you know someone who's really good at Google Street View. And I just said doxing on stream, so I should not point the camera out of my actual window. Oh my goodness, why am I like this? Right. Thank you everyone for another week where we try and work out what on earth a maths live stream is. What would it mean to do maths on Twitch? Somebody noticed that my logo got messed up. We're like in the palette swapped universe. I have this logo, which is supposed to look like this, white, pink, blue, but in like the one of the many things. That's one of the things, by the way, that broke. That's backwards, or is it like the wrong way up? I'm gonna try and fix that. Oh, it's like a puzzle. Whoa. Oh, I've made myself a little puzzle. But it's supposed to be the other way around, right? 3. There's only 6 permutations, come on. No. 3. 3, 2, 1. Yes! Logo! Did it. Solved it. Right, good. Okay. I'm actually going. My website link isn't working. What? This one? That one works for me. Oh, the one on my Twitch. Maybe. I did type that one in a hurry. What have I done wrong? This is good stuff. Oh, I've got to follow a goal. I've got stuff. Oh, in here. My very basic website is a 404. Yeah, that's a 404. Why is that 404? What have I done wrong? Wait. Oh, I've put .html on the end for no reason. Cool, right, okay, I need to delete the HTML from my Twitch link. This is fun, isn't it? This is the sort of thing that you just... Yeah, we made 100 followers. We have a follower goal of 128, at which point nothing happens, except I don't know, double it or something. Good. Yeah, sorry. Oh, the other links in that section. It sounds like you found links to my research work, all of which was done at Cambridge. Also loads really slowly. This is a service that Cambridge offers where you can just download people's PhD theses. They launched this service as like an online repository of everybody's PhD thesis, and Stephen Hawking's thesis immediately got 1 million downloads, because of course it did. And as far as I know, the service is kind of just, would you like Stephen Hawking's thesis? I think to this day, it's still, yeah, we host all of the theses on this online. Yeah, Stephen Hawking's over there, that way. Like a library that's like only got one book that people want or something. But also my book. So good, right. But Stephen Hawking's book as well. So you can grab a free copy of Stephen Hawking's thesis, and everyone has. Good times. Right, okay. I've said I'll end it multiple times now. Probably should. Right, good. Okay. Yes. Calling it a day at 4:20. I will see you round next week. Take care. Bye. The stop.